continues a topic that we started a little bit yesterday. So we started with planar graphs and other types of graphs, schematic drawings, then moved to contact representations, which were useful for displaying statistical data and maps. And today it's a topic that is purely based on maps and placing labels in maps, and we will see that this is a very geometric type of problem, and then I will show you some of the results here. So map labeling by itself is a very old problem, because people have created maps by hand for centuries or even longer. And of course there's lots of experience of cartographers on how to place maps. And this is just a quote from a Swiss cartographer that is already kind of 50 years old or so, almost, who said that if you do the label placement wrong, then it can spoil the entire map. Yeah? So even if your picture in the background is very nice, but you place the labels amateurishly, then the map is not good. And of course, there's, yes, as I said, there's a long history of criteria of how to place labels nicely. This also depends a bit on culture, and maybe in Iran, because you write from right to left instead of left to right, maybe it's slightly different. In Europe, at least, the preferred position is, say, the top right of the point that you want to label. Maybe here it's top left. So these are some of the guidelines. It should be close to the point. It should clearly avoid covering underlying features of the map. So if there's a small lake or like a tiny river, you don't want the label to go over this, because then people cannot see the lake anymore. But clearly you also want to avoid overlapping of different labels. So if you have two label names or two city names, they should be placed in a way that they don't intersect. And for reading the map, it should be also graphically clear whether a label belongs to some point left of it or right of it. So distance between label and point matters. That's a picture of a map created by David Imus, who's a cartographer in the United States, who created like a new map of the United States completely by hand in over 2 years of time. So you can see how much time it takes to create like a very nice map. And here, if you, for example, I don't know, pick any label like this Ketten ring here, the only point that is close to it is that one to the right, so it's kind of very clear what is the association here. This type of problem of placing labels in maps has been translated into computational geometry community quite a long time ago, already in the early 1990s. People have studied label placement, and we will see how this has developed over time. So typically the geometric labeling models are as follows. You can abstract the map into like a point set, so you're given n points in the plane. Imagine there are cities or other places, and you want for each point to put a label that gives the name or some description of that point, but we can model this as the bounding box. So it's points and rectangles, basically. The goal now is to find a feasible label placement, and there's a little star because we have to explain what feasible means. For example, for a maximum subset of the points, so that no two labels overlap. Yeah, so just imagine this as a kind of maximization problem of you want to put as much information as possible, leave out any city, but of course if you have a situation like that one where there's just not enough space to put all the labels, then maybe you can only label 4 instead of 5. A different type of problem that has also been studied, but is maybe not so relevant in the application, is the maximum size problem. Here you can imagine if you shrink all the rectangles basically to like a epsilon size rectangle, then clearly you can put all of them. Now the question is, how much do you need to scale down the labels so that you can still fit all of them? Yeah? And here you see we can fit all of them if we make the font smaller. If it gets too tiny, it's a useless map. But for some limited range of font sizes, maybe that's an interesting problem. So we need to define what is a feasible placement of that rectangle with respect to the point that should be labeled. And basically in the literature you can distinguish two types of models. There's a bunch of discrete models and there's a bunch of slider or continuous models. So in the discrete models, usually you have a small set of candidate positions for the label. For example, you could say only top right, and then there's no choice. Or you can say to the right of the point, or one corner should touch the point. There's also 8 position models that are frequently used, when you can also center the label around the point. But more than 8 positions is rarely used in a discrete model. Then you can also say, okay, maybe we don't care how the label is close to the point. Let's be able to move that label completely around the point. Yeah? And these would be slider models, also coming in different flavors. Of course, you can imagine that this is a subset of positions of the slider models. So any solution that you compute here is also valid here, but maybe you can place more labels if you allow some shifting. This is a slide summarizing a little bit what is known about this, this kind of static label placement problem, where the input is a set of points, you know the rectangles, you know their sizes, now find a good subset of labels. So basically all of these problems are NP-hard optimization problems. So there's no efficient exact algorithms that you can hope for. And this has been shown in a series of papers starting with Forman and Wagner at Sausage in '91. That was basically the paper introducing this into computational geometry, and then many people continued working on this. So they studied all kinds of discrete models, slider models, everything is hard. So if things are hard, you need to do different strategies of coping with the situation. One of them is to study approximation algorithms, and that usually works reasonably well for labeling. So for example, there is an n log n times, or pretty fast algorithm getting you a 1/2 approximation for unit height labels. So now you can think maybe unit height is kind of a strong restriction. But for text names, it's usually not that much of a restriction, because if you say every city gets the name in a single row, in a single line, no line breaks, then this is unit height rectangle, because our font has a certain height and we can vary the width. So that's kind of useful, and there's even a PITAS if you want to go closer. There is an algorithm that provides a log n approximation. But the good thing of this is that it works for arbitrary rectangles. So you not have this limitation of having unit size. And this is like 10 years ago. There's also many practical exact algorithms using, for example, some branch and cut ideas of how to get to the optimum by not exploring the entire search space, or using integer programming. We've seen, I think 2 days ago, like how you can use integer programming to model geometric situation. And of course, because this is a very practical problem, there's lots of heuristics that try to place many labels, but there's no guarantees of how many they are. If you go to the slider models, then there's also an n log n time approximation with approximation factor 1/2, now for arbitrary rectangles. So that's kind of good. There's a PITAS for unit height rectangles, which is also kind of mirroring what we have seen here. And likewise, there's exact algorithms and also a bit of heuristics, but the application people like more the discrete models than the slider model. So that's a bit of the summary of the state of the art, say up to early 2000s. And then if you think of maps today, probably few of you would think of paper maps or atlas, but many think of like the smartphone and the maps that you have there for finding your way in Tehran, or for ordering a taxi, or things like this. So if you think of maps today, they are usually, or many of them are on digital devices. And that means that they are also not this one map that is published every 10 years showing the geography of your country, but they are now way more dynamic. So new information can come in. They can be individualized, so you can filter your map for, say, restaurants of particular cuisine in your area, and then it's always a different set of labels that you need to place. And such maps, it's hopeless to do manually. You cannot have people doing that on demand. So clearly we need algorithms, but if you think of digital maps, then users can also do kinds of modifications with the map. It's not longer a static picture, but you can zoom, you can translate, move in the map, you can even rotate. So sometimes if you have a car navigation system, it always follows your heading of the car. You can tilt the map, sometimes you want to see perspective. So it's all kind of operations that mean that the layout, and in particular the labeling, must be adapted to this kind of dynamic movement. So one thing that is a big topic is how to basically compute the geometry of the map content. So how do the roads look like? How do you represent mountains, buildings, cities for different scales, and what happens if you rotate? But this is not the topic of today's lecture. We will look at how to adapt the labels if you do these kind of dynamic operations. So the first thing is, we know a lot about static labeling. Can we not just use these methods? adapt them to maybe a temporal dimension, and then we should be fine. So if you look at the static labeling problems, what they usually do is they model this as a conflict graph. So you take, for example, 4 points in the 4-position model. So there's 4 rectangle candidates for each label feature, and you need to choose one. And we want to choose one so that no pair of rectangles intersects. This should be a graph problem that you know very well. It's the independent set problem. Yeah? So if we represent every of these rectangle candidates as a vertex in the graph, and we add edges if these 2 label candidates cannot be chosen together. Then you see for each label feature we have a small K4 graph here, simply meaning that you don't want to place the same label twice. Yeah, so you need to choose at most 1 point from each 4 cycle of K4. And then we have edges if 2 rectangles intersect. So for example, this top rectangle here of the lower left point intersects 2 labels here, 2 candidates here, and 2 candidates here. Yes, and this has 4 conflict edges. Okay, that's how you go from the rectangles to the graph. And then they use, I mean, of course, independent set is also an NP-hard problem. So you use some kind of greedy strategy or other heuristics to compute, say, large independent sets. And this would be your set of labels to place. So if you want to adapt the same approach to dynamic maps, what you need to do is that you have different frames of an animation if the user zooms or if you do rotation. And then if your methods are fast, you can say, okay, this is the next frame. If I compute this in a few milliseconds, it will be fine. Using some heuristic on that type. So one approach that you can find in the early literature is to basically expand or augment this conflict graph with additional information of when, at what scale levels a particular conflict arises. So this is, for example, the label of Essen and Dortmund, 2 cities in Germany, and then the label that you see on the edge tells you for which map scales these 2 would interfere. And then when you want a particular zoom level of the map, what you can do is you can query that particular conflict graph to get the one that is relevant for your conflict range, and then apply some greedy label selection procedure. A different approach is kind of fast on-the-fly computation where you do not do pre-processing. They use some kind of strategy to compute this conflict graph on demand whenever you see a new view. Then they estimate costs for possible label positions, and then by priority of the labels, so maybe you want to start with the capital and the cities that are big cities in the country, then in descending priority order you select the best currently non-occluded position of that label, if there is still one. So it's kind of a greedy strategy using priorities and these kind of cost values here. And this can be implemented pretty fast. So in less than a millisecond, for like 1,000 labels in the map, you can do that. And this was 2007, so with today's hardware, it's even better. And then another similar approach uses so-called particle-based conflict detection, where they start with a 4-position model, but if all 4 positions have a conflict, then they move to an 8-position model, try more positions. If you still have conflicts, you go to a slider model. If you don't find anything here, you can even move the label a little bit away from the point. And then again, in priority order, you can try to do this. It has a bit more candidates to consider, that's why it's slower. It needs up to 10 milliseconds for 1,000 labels, but it's still kind of fast enough to do this on-demand computation if it gives you a good result. So the question is, if we have these practical methods, what is to be done for theory also here? Is this the right model? So yes, there needs to be done something, because dynamic maps are not just independent frames of static maps. Yeah? These approaches are fast enough for real-time labeling, but the animations that you get when you just decompose all the frames into an animation, they are often of very low quality. And this is because you compute each frame independently of the adjacent frames. So you might have at 1 second a set of labels, and then the algorithm computes the next frame, and it might be not a completely different but a very different frame. And then you go to the next one, and maybe then something from the first one reappears. So you get a lot of shaky animations here. So labels, I will show you some videos to show this. So labels start to jump or to be turned on and off shown or not shown. And all these methods do not consider any kind of temporal coherence or consistency over time, so that you try to avoid that labels behave strangely over time. And this is the point where I want to show you two small movies. This one is from a car navigation system. It's a bit maybe 5-6 years old, but you can see that all the restaurant labels they start to be very shaky. Sometimes they appear and disappear. Let me play it again. Stop. You can see what happens here, and this is clearly not an animation or labeling of the map that has a very high quality. It's not maybe not fully state of the art anymore, a few years old, but you see that the problem is there if you don't pay careful attention to that. The next one is using Google Earth, where I put the city names of a small state in Germany, and what I want to show is what happens when you zoom and when you rotate the map using Google's labeling strategy here. Of course, this is a difficult set because it's very dense, it has lots of labels, but you can see that if you start moving, then labels sometimes overlap, they start jumping. So for example, Saarbrücken, which is the capital here, sometimes even disappears. Here it's back again. Now it moves here, it moves here. So you see that there's problems if you... Sorry? Sometimes they have overlap, but they try to, at least if you stop the animation, do overlap free, so that is guaranteed. But during the rotation, there's a lot of movement, and that's distracting if you need to work with that map. Yeah? Okay. I think not much is happening here. But you get the idea. We need some models that make sure that over time the labels basically stay at their location and do not turn on and off too frequently. So in the first paper on dynamic map labeling from 2006, Bean et al. Described a number of criteria that you might want to apply for making dynamic labelings nicer. So for example, they say that if you zoom into a map, so you search for more detail, then labels should not disappear. Yeah, because you search for more, and then if something disappears, it's strange. This is maybe you can weaken this a little bit, because at some scale you don't need the country names anymore when you go to city level. Yeah, but usually if a restaurant, for example, is at some scale and you zoom in, you don't want it to disappear. Yeah? And when you zoom out, then it would be strange if somehow a label appears, because you want less information, you want a more overview, and then suddenly more details come. Yeah? They call this a monotonicity criterion. Then what they say is that as long as a label is visible on the map, it should not change its position or size non-continuously. Yeah? So maybe you can scale it or slowly move it, but not jump from the top right position to the bottom left position. Yeah? Then this is history independence criterion, that if you move to the same location of the map from different starting configurations, the map should be the same. You can ask whether this is necessary, but if you want to, I don't know, you remember some piece of the map and a certain point of interest was labeled there, and then you want to show it to your friend and you come from a slightly different place and then suddenly it's not there anymore, that would be kind of weird. And then the label size on screen should mostly be invariant, so when you zoom in, then you have basically a smaller portion of the space on your screen, and if you don't adapt the label size, they would kind of, when you zoom in, become very large, right? And that means you should then shrink your labels so that on screen they have the same constant font size. And this was, for example, done in the Google Earth example. All the labels had constant font size on screen, but relative to the map background, they changed their size. Okay, so if we want to model this, we're still given a rectangle with a set of points in there, and we want to place features. Yes, question?
Just one question. The importance of each label does not matter here. I mean, the name of a capital, for example,
yes.
So I guess that should be present all the time, I guess.
you're right. What I described next is basically for unweighted points. But most of these methods can be adapted having priorities, so some labels are more important than others. The only problem is that when it comes to approximation algorithms that I will show you in a few minutes, then if the priorities of labels play a role, you cannot have this kind of argument for the approximation factor anymore. That's important that every rectangle has the same importance. But yes, you're right. Okay, so we have these labels. That's of course not a nice placement. We want them to be non-overlapping. We want them to be close to their features and maybe be unambiguous. Here it's not so clear whether label 3 belongs to that point or that point. You need to do a bit more thinking, but like that the corner points more nicely. This is all kind of criteria that we know from the static labeling that I've started with. Yeah? And one optimization goal could be to maximize the number of labels, so solving geometric independent set. That still applies to all the labelings that we want to compute, so this doesn't get invalid suddenly. But now if you do zooming and you don't change the font or adapt the font size, you see that the labels become small and at some point unreadable, so they need to keep their size on screen. But because the point set shrinks, suddenly labels start overlapping that were not overlapping before. Yeah? So new conflicts arise when you zoom out of a map. Also new points come into the view, so you need to adapt to external labels that are new. Yes, so for example, these two need to be removed in order to have a valid labeling at that scale. And if you do rotation, then similar things can happen. You have a valid labeling here at one scale, you could place 5 labels, but if we start rotating, well, this is not what you want to see in the map, right? Because at some point you cannot read them anymore. Yeah? So we want that the labels stay axis-aligned rectangles. And then you do the rotation, but of course the point configuration might then move into an angle where 2 labels start to intersect that were conflict-free before. So depending on the rotation angle, now you get new intersections. We need to define when to show a label and when not to show a label. So basically when you do rotation and zoom, we have additional dynamic criteria that mean that, for example, we don't want the label to jump, and we don't want to show a label, not show a label, show a label, not show a label if you have a short period of movement. So that's the criteria, and we will look at exactly these two problems now. What happens if you have a map where you can zoom, and what happens if you have a map where you can rotate. Okay, so for dynamic zooming, this is the labeling model that was proposed in the first map labeling paper using dynamic maps, which basically is a 3D model where on the third axis you show all the maps at different scales. Yeah, so you have the XY plane, which is a map at a particular scale, and if you move on the Z axis, then you get different scale maps. So yes, I said that if you take a horizontal slice, it should give you the correct map for this particular scale. And now the question is what happens to the labels in that kind of 3D space. And you see that they look like pyramids with their apex on the ground plane. What that means is if you go to higher levels in that model, it seems like the label boxes are large. They cover more of the space of the map. So this corresponds to a map that is at a small scale, so maybe shows countries of the world or the national map. If you go further down here, you get more detailed maps. So you have on screen, you show a smaller portion of that. And then the labels can be relatively smaller with respect to the map and still give you a conflict-free labeling. Does it make sense? Yeah, so when you move up, you show a larger portion of the base map on screen. Labels need to be larger because they are shrunken more. And if you're further down, you don't need to shrink that much and the labels can be smaller. So that they have constant size on screen. And this actually defines these pyramids. At the same scale, at least if we have unit height rectangles, for example, then all the intersections of an intermediate plane that you cut out, all the labels have the same height and maybe the width is different. Okay. So one simplification that is done here is that the labels are basically in a one-position model. So we we do not allow the labels to maybe choose between top right, top left position. They are centered at that point currently. This, of course, is a restriction. You lose some kind of freedom to maybe show more labels, but it clearly means that if there's only a single position available, labels do not start to jump. Yeah? And then the second criteria is that they should not flicker and start to move. So this is a kind of a schematic view. If you think of these pyramids from the side, so like taking away one dimension, you have the scale on the vertical axis and maybe the point distribution or projection on the right. Then these pyramids become triangles. And for each label, we now have an available scale range where we can show that label. So maybe it makes sense to show a particular restaurant only at scales where you see the street level of a city and not if you have country level. And this we can model by having a vertical interval of when a label first becomes available and when it should no longer be displayed. If you don't make this extra information, then you can show every label all the time. But if you move this, you can have these trapezoids basically that show when the label might be selected. So you can take away the rest. And now in order to avoid this flickering, so showing a label, not showing a label when you do monotone movement, one way of achieving this is saying that for each label we want to select a single range of scales where the label is shown. Okay? And this range of course needs to be a subset or sub-range of the available range. And it's marked here in blue. So for example, what you can see here, if you take these two trapezoids, they are independent until that point, then they start to intersect. This means that if you zoom out further, these two labels would overlap, and now we need to make a decision which one to keep. So it's kind of an intersection over time or zoom level. And then the analog of maximizing the number of placed labels would simply be to maximize, well, you can see this as an integral going over the zoom levels that you might have and maximizing the number of labels at each zoom level. But because this is kind of nice and discrete, you can show that this integral way of maximizing the number of labels is exactly the same as summing up the ranges that you select. So the sum of the blue heights here. This gives you the number of labels for a monotone movement from 0 to infinity, basically. Yeah, that's the model. Questions about the model? Okay, so first we studied the complexity of this problem and showed that it's an NP-hard problem to decide for some given k whether we can find a feasible labeling that has at least this value k. And this even is true if all the labels are available all the time, from 0 to z max. The proof uses again planar three-sat reduction, like the one that I've shown yesterday. So you already know this kind of idea of having the planar graph of a three-sat formula and all the clauses connect from top and bottom with the three legs. So this should remind of what you've seen yesterday. I will just sketch the proof, not go into very much detail, but it's kind of interesting to see what happens. And what we need to do is model somehow how a variable works and how a clause works. So this is basically what we need to do is find a set of points in the plane and create these label pyramids for these points and see how much active range sum we can collect. So these points all live on an underlying grid, and they are formed in a way that when you grow all of them simultaneously, then at half of the maximum z value they start touching their neighbors. Okay? So these live on grid cells, and if you start growing at a certain height, the pyramids will start touching. So what this means is up to that level you can show all the labels. And now you need to make some decisions. And actually if you want to maximize, because you see this blue thing forms a cycle of an even number of pyramids, there's basically two configurations that give you the maximum weight. The green configuration, which I don't know where we start numbering them, but if this is position 1, this would take all the even positions and let them grow until they touch at the next level, and this is actually the top level that we have here. Okay, so this would, every second pyramid now has the full label height and every other pyramid has half the label height. And in this green cycle, that is the best you can do, unless you flip odd and even rows. Okay, so these are two configurations of this part that have exactly the same value, and you cannot do anything better. That's because the way of how they are placed. And you see at some points we can connect either true or false literals, and this will pass the information that you made for the variable into the clause. Okay, so you can see if you have something that is true, we always put this in green, then the tall pyramid is basically towards the variable, and the small pyramid is towards the clause. Okay, so the information flows like this. And if you have something that evaluates to false, it's the opposite. So the way we can use this now is when it comes to bringing three of these truth values together, and then we should get a higher value if at least one of them is true, and a smaller value if all of them are false. Okay, so these three yellow pyramids is basically the core of the clause gadget. And first let's think of three literals coming in, all of them are true. I said when they are true, then the last one or the even positions are small pyramids. Okay, and now you can think yourself how much more can you do with the yellow guys. Currently three of them are at half the height. Well, you can choose one of them and grow. But no two of the yellows can grow higher than half the size. Okay, and we have a set of three of those, so we can choose which one to take, and they will have the same value for the objective function. So right now, this guy here is tall and the others are small, which means that we can afford to make that one that one false, because it still fits. Here they don't even touch. Now they touch perfectly. That's fine. You can make that one false, but if all three are false in red, then you get a problem here. And the way to solve this is that either the red or the yellow one need to go to half the height. Yeah. And this is where you lose a bit in the objective function. Yeah. So we know if everything evaluates to true, if it's a satisfier for formula, then we know exactly how much contribution we have. Yeah. So the clauses all give 2 Z max values and the rest is constant. And if something is false, then it's just 1.5. Then we can define our decision value k in such a way that we can recognize whether all clauses have 2 Z max, then we are happy, and say the formula is satisfiable, and otherwise we say it's unsatisfiable. And this basically is the idea of the reduction. Okay? So we know it's hard. What we can do is try to achieve some approximation algorithms. And the one that I want to show here is basically a very simple idea to greedily top-down sweep over this 3D model and assign some active ranges to the labels, and then we can see how much of the quality we achieve here. So our input is a set of open label pyramids. For each of them we know their available ranges, and what we want to compute is active ranges for all of those possible labels. So initially we say that every label is active the entire available range. Of course, this will have conflicts. Yeah, so we need to adapt this. But we start here, and then we put all of them into a priority queue that is ordered in decreasing order lexicographically using the currently selected active upper end and the available upper end. Okay. And then as long as this queue still has elements, we extract the maximum possible pyramid. So that's the one that we can start filling from the next top position. We do that, and then we need to update other label pyramids so that they are not in conflict with the one that we have currently selected. Yeah, so we go over all other labels that we have not decided yet, see if they have non-empty intersection with the one that we just chose, and then we need to update the upper end of the active range. And this we put to the minimum of the current value and this value SEE prime, which is simply the largest scale at which these two labels still can live together. Okay? So you see E and E prime intersect, and you look basically for the intersection point of the pyramids, and this is the scale when the other label could possibly be activated. Okay? And if at some point we lower the upper end of the active range to the lower end, then this label is never shown and we just delete it. That's the idea here. Just on a small projected example, you start with the topmost label, you select this completely, until the bottom, and then we update all the other labels to the topmost position that is still feasible together with the red label. Then we go to the next one. In that case, we can fill to the bottom. We don't need to update anything, and here we're done. So this idea is not an optimal solution. Maybe you see one that is better. Yeah, so we can slightly move these two. It looks like liquid in glasses, right? We can move these up, and then you have more height here. Because these two can live together for a while the solution just showed one of them. Okay, so this algorithm that we have here certainly computes a valid labeling in the sense that we have no conflicts in the end, because we made sure that we remove all the conflicts. And if you don't worry too much about efficiency, you can do this in n squared time and n space. We'll do it slightly better in a few minutes. So to get the approximation factor, something that is useful is this so-called blocking lemma. So it takes a set E of, think of label pyramids, but we call them more generally extrusions as 3D shapes. And if it's true for the configuration that we have, that every pyramid that you take blocks at most C pairwise independent other blocks for all Z values. Yeah, so when you select one, there's at most C independent that you could have chosen instead. Then the algorithm that we had seen here gives you a 1 over C approximation. Yeah, so if you think here, basically this one blocked two independent ones, so it could be a 1/2 approximation here. And if you have 3D shapes, then we need to find out what is this value C. But if this is true, this blocking lemma, it immediately gives us the approximation factor. In terms of terminology here, we spoke about blocking. So one of these selected labels blocks another one at a certain Z value if at that Z value E is active. So S is between small AE and big AE, and the two, we call them traces, so which is the intersection of the pyramid with a particular XY parallel plane, if they have an intersection. Yeah, so basically at that particular scale that you selected, the two labels would intersect. This trace is simply just taking the pyramid and taking a slice at a particular scale. And we say that two labels or extrusions are independent at a certain set value if their traces have empty intersection. Yeah, so if you take the map at that scale, they are disjoint rectangles. Okay, and then the proof of this blocking lemma is that basically all the labels initially start with the maximum active interval at all. Yeah, so we say every selectable range is the active range. And we only decrease the upper bound of the active range in order to avoid conflicts, because we have already selected something else. That means that if some of the label is inactive at a certain scale, there is a reason for it. There's a witness, some other label that blocks it at that particular value. Otherwise, we would not have decreased. And now if it is true, as by assumption, that every of our selected label blocks at most C independent labels, then of course the optimum solution at any slice that we take out can have at most C times more labels than the one that the algorithm computes. Yeah? Okay, so that basically is a tool for giving us the approximation factor. And now we need to give an algorithm that helps us to do this a little bit faster using maybe also geometric data structures. And the claim here is that if you have n axis parallel uniform labels, so right now think of maybe unit squares or rectangles all of the same size, then we claim that this algorithm computes a 1/4 approximation. And we can implement it in time n plus k log square and n log n space, where k now is kind of output sensitive parameter that gives us the number of actual phase intersections of the pyramids. Yeah, so if everything is so disjoint that they never intersect, then k is small. But if everything is completely dense, it can grow up to quadratic. Okay, so for the proof, first of all, we want to find out what is the C for our particular situation. And since we know that all labels are uniform, then we can see how many independent labels we can place so that they still be blocked by the same label possibly selected by the algorithm. Think of unit squares or unit rectangles, and then it's easy to see that you can place at most 4 that are independent. If you try to squeeze in a 5th one that has the same shape, it will not happen, because you need to move 2 of them so far away that it can intersect that one of them is not blocked anymore. Okay? So that's why the approximation factor 1/4 comes here. And now how to compute this? Faster is by using kind of a lazy update strategy for the conflicts. So we use a range tree. I guess you all know range trees very well from the computational geometry courses. And these store points, and we can query for the points intersected, contained in some rectangles. And what we store here is the tips of all the pyramids in the ground plane pi 0. Okay? And then the lazy update works as follows. So we do our loop taking the next element of the queue. But since we do lazy updates, we are not sure whether the one that we pick now can actually be used. So we do a check whether the current active range is a valid one without intersections. If yes, then we set it active. If no, then we forgot to update or to lower the upper bound, and then we do that accordingly and reinsert it into the queue to consider it later. And now what's missing is this check whether a particular range is valid or not. And this we can do by querying this range tree that contains the apexes of all the already selected labels. So we have placed some labels and they will be there in the plane, and the question is, can we add a new one? And what we do is so basically the yellow one is a label that has already been placed, but we don't put the labels into the range tree, we put the center point of the pyramid. And now we want to know if this purple label here can be placed together with the yellow label. You see they cannot be placed together, they intersect. In order to find out this from the ground point is by taking a rectangle that has twice the side length of the label that we want to place and do a query in the range tree. And then if the point of the tip of the pyramid is contained here, you know that the distance is so close that up here they will intersect. And if it's outside, we're happy. Okay? And actually we know that our result with this query rectangle has at most 4 points. That's because no more than 4 independent rectangles can intersect the same guy. So our answer set is small. And how many queries do we do? Well, for every kind of event that we have here in our pyramid situation, and the events can be intersection points of labeled sites, so this is the K, or just the upper or lower range of the pyramids. And each of those queries we can do in log squared time. And then when we select a new point, of course we have to add this to the range tree, so dynamically update what's contained here. So that's the idea, and basically concludes the proof of this theorem. Okay, so there's also other types of approximation algorithms. If you, for example, do not have uniform labels, all of the same size, if you have arbitrary square labels, or this also works for arbitrary rectangles with the same aspect ratio, then the approximation factor goes down to 1/24. But that's kind of the trade-off that you have to live with when your rectangles get different size. Couple of open problems for this labeling in maps where you can zoom in is that currently we do not know whether there is a PTAS that can get better approximation ratios here, like 1 plus epsilon. We have also not considered k-position models. Maybe 2-position models would be something that is interesting here, or using sliding models. And also we made this very strong assumption that labels cannot move at all. So what happens if you would allow continuous label translation? So you can imagine that at some point 2 pyramids start intersecting, but if there's space to move both labels to opposite sides, you could still keep both labels for a little while. Yeah, some models like this are also not yet studied well. Okay, questions about the dynamic zooming so far? Then for the last 15 minutes, let me look at the second type of dynamic operations that you can do with maps, namely rotation. So here, again, remember we have our labeled map. We want to rotate this, keep all the labels axis aligned, and you see at some point labels start intersecting, and then we need to decide which one to pick. Yeah, that's the model. But we can take a different perspective on the same model by not rotating the point set and keeping the labels axis aligned, but rather keeping the point set kind of axis aligned or fixed and rotate the labels. So this, of course, you would not do in the map, rotate the labels, but the type of conflicts that you get is exactly the same. So if you start rotating the map here to the left, it has the same type of conflicts as if you rotate the rectangle to the right by the same angle. So the point when they start to touch, that's exactly the same here. So then they stay in conflict for a while, and then they become independent again. Okay? So for our algorithms, we can also work with a model where we have a fixed point set, and we see what happens with the conflicts if we rotate the labels 360 degrees around. So that will be on the next set of slides, but always remember that we transform this solution, of course, in something with axis aligned. So this is the constraints that we have seen before. So no label should occlude, so no labels should overlap, but also we do not want to occlude one of the point of interest. So maybe there is some kind of city icon like a red dot, and if the label would move over it, you don't see that anymore. So in that sense, we do not want to occlude any of the input points, and then we should not have jumping labels and flickering labels. So jumping means something like this. So you have a conflict and you suddenly move it to the left. This we disallow. And we can obtain this in a similar fashion by saying, okay, all the labels are anchored at a particular point of the rectangle, and this is what we can do. And the flickering means that if they are in conflict and have the same priority, we could choose either of them, and it gives us just the same value. So if you're not careful, then they always alternate, and this we want to avoid. And by doing that, in a similar way for the zooming, like for the zooming we say, we want to compute an active angle range, so say from 20 degrees to 148 degrees, you show that label, and that's it. In that sense, you take your label, and maybe you mark in blue when it is shown, then it's not shown, and here it might be shown. So we have a cyclic angle interval compared to the zoom interval that we had before.
It's connected.
It's connected, yes. So a single interval starting at some angle and stopping, and of course we go modulo 2 pi.
And in the background of the label, quickly transparent? I mean, in terms of not moving that point?
Aha, like this? Or
Not mean the back, I mean it's a box, right?
we model this as a box, but of course in the map it would be the name of the label. Yes, and if we have a labeling that fulfills this kind of thing, so not jumping and a single active range for each label, we call this kind of a consistent or temporal coherent labeling. So if you state like the computational problem behind this, we're given this map as a set of points. We want to find a consistent rotation labeling that maximizes, again, the total length of all the active ranges. Same objective function as before, but now these intervals are angle ranges. Yeah? And what we optimize is one full rotation of the map. So one variation that is, you could also try to maximize the smallest active range, so have no label that appears just for a very short time. That's a typical variation of an optimization problem. Both of these problems are hard. It's no surprise in labeling. And this max-min is even hard to approximate better than 3/4. So that's APX hardness. I will not show you the hardness proofs here because we have already seen one, but rather go directly to an algorithm for getting an approximation ratio here. And the first thing is this so-called conflict lemma. So if you have two labels L and L prime, and for now we model them as unit squares, but later we can change, then we can say there's a set of conflicts of these twos, and the conflicts are modeled as contiguous ranges of angles. So why is it at most 4? So imagine you have two labels and you start rotating them. So at some point, two of the sides collide, and then for a while we have an overlap. This is marked green here on the circle. Then they are in parallel again, and for a while now they will be conflict-free, so that's black. Maybe this relates to your question. Now this label starts occluding the input point, and in that situation it's clear how to resolve the conflict. We need to not show this label and show this label. We mark this as a red conflict on the side, then we have another green conflict and another red conflict. Okay? And this is why if you consider only a pair of labels, you will have 4 forbidden regions or something where you need to do, and for the rest you can show both of them.
There are at most 4 components.
Yes, 4 components. We also speak of soft conflicts when just the labels overlap, and hard conflicts if a point is occluded, and like I said, then the decision is clear. Then we can also, because we will use kind of potentially discretized version of assigning these ranges, we can speak of events when some conflict occurs for the first time, and an event when the conflict appears for the last time, and then if you rotate a little epsilon, it will be independent. Yeah, so these will give us angle or rotation angles for which something needs to change. And there are, because we have at most 4 contiguous ranges, there are at most 8 conflict events from one pair of labels. So if we want to take the global view now, we have one pair. This gives us 8 conflict events, and you do this for multiple pairs, so you would get more conflict events. But for every pair, like 8. Okay. So if you just think of a brute force algorithm, what you could do is compute all the conflict events. So take all pairs of labels, see when they intersect. For each so this gives us a quadratic number of these label events on the circle, and then for each label we need to decide when to show it. What you can show it never makes sense to let start a label in between 2 conflict events. These you could always change to like a canonical labeling with the same value that starts at one of the discrete events. That's a standard trick you can do. And because you can choose any pair of these events as a potential candidate for active range, this gives you n to the 4. Yeah? And then if you go over all combinations, you will find the best labeling. But of course, that's exhaustive search. So we want to do this slightly more efficient and using some kind of ideas for getting approximations here. So observation 1 is that if you have disjoint subsets, for example, split our label set into the red labels and the blue labels, and magically from some oracle we could get the optimum solution for blue and the optimum solution for red, then one of them is a 1/2 approximation for the global thing, right, by pigeonhole principle. So if we compute the optimum solution for red and for blue, and we have just 2 solutions, and one of them must at least have 1/2 of the optimal value. If both of them were smaller, then that doesn't make sense. Yeah? And if generally you have k of those subsets, then it will be 1/k approximation. So the next observation is that, of course, the spatial positioning of the labels matters whether they can at all be in conflict or not. Yeah, so if you have 2 labels, we can think what is the distance of the anchor points that is needed for them to be in conflict. So if you see that this label rotates around, you know where the tip is, and if these 2 circles are intersection free, then we can choose them independently of each other. So if this distance d is more than 2 times the radius of that circle, then they are independent, and if it's smaller, they could be in conflict. If we think of these labels as unit squares with side length 1, then the radius here will be square root 2. Okay, and if d is more than that, no conflict is possible. And now we can use a technique that people who've worked a lot in computational geometry know very well, like this line stabbing technique for approximation algorithms. So we can stab now our complete set of labels or circles with vertical lines whose distance is 2 square root 2. Yeah, so this distance bound. And then we color each label by the color of the parity of the line, of the stabbing line. Yeah, so the odd stabbing lines are blue and the even ones are red. And this gives us a set of blue labels and a set of red labels. And note that no blue label can ever intersect, no 2 blue labels can intersect each other. Blue and red could still intersect. You do the same trick with horizontal stabbing lines of the same distance, and that colors the labels yellow and black. Now each label got 2 colors, yeah, and this defines 4 classes here. So there are some labels that have received red and yellow, So those that are stabbed by a red line and a yellow line, these are these three here in this example. If you go to blue and yellow, then this is a different set of labels. You can go to blue and black and to red and black. So now we subdivided the set of labels into 4 disjoint groups. And now if we can solve each of them optimally, the previous observation gives us a 1/4 approximation. Okay, this is using the so-called stabbing shifting technique that is well known by Hochbaum and Maas. Yeah? That's the idea. And now, what do we have? We have we make the assumption that the density of points in one of those squares of fixed side length is bounded. So imagine there cannot be too many labels in one of those squares, otherwise it wouldn't make sense to have all of them in a map. Alternatively, you can say that maybe you start with a map that is not meant for rotation, so you would have a valid intersection-free selection of labels here, and now we ask what happens if you start rotating. So this is kind of a bounded size instance. And so we know that there's just a constant number in there. So we had this discretization lemma that told us how many possible candidate ranges we have here and how many combinations. So if we have a constant number of labels inside the square, then of course the number of conflict events that we get is also constant. Yeah? We know that there's at most 8 per pair. We have at most a constant number of labels in each square. So this gives us a constant number of conflict events that we need to consider. This means that even brute force we can solve one of those instances optimally. Okay? So here, let's zoom in. Conflict events is constant. For each label, the number of range candidates is constant, and we can just go over all possible combinations for this tiny instance. Okay? So in that sense, we have the following result, that there exists a 1/4 approximation algorithm for this max total problem, and we claim that we can do this in n log n time, because all this solving of tiny instances, that can actually be done in constant time. Okay? Now you can extend the same idea to get a PTAS simply by making the stabbing lines more spaced. Okay, so here this is what we've done so far. Every second line is deactivated, but now you can take every kth line, delete it from the set, and then every of those gray squares is independent from each other, because they are so far away that no label here can have a conflict here. Of course, the gray instances get larger, so you need to spend more computation time to solve them optimally, but you can use the same idea, go over all possible parities of which one to deactivate and choose the best one, and this will give you, if you choose the k correctly, give you a 1 minus epsilon approximation. Yeah, so there's k² possible combinations for doing that. If you choose k to be 2 divided by epsilon, then this trick gives you a 1 minus epsilon approximation. And the approach here is, because I'm kind of at the end already of the time slot, let's just do that very quickly. The thing is that here now the number of labels inside the square grows with 1/epsilon squared. And hence the number of conflict events also grows, but that will just go into the running time. Yeah, so now we have 1/epsilon to the 4 range candidates to consider, and the running time that you will get in the end is n times 2 to the 1/epsilon squared log 1/epsilon. Okay, so this is basically the theoretical result, that we can have a 1/4 approximation in n log n time. If you want to have a PTAS, you need to spend more time. And let me just say that the same idea also works for other shapes, as long as they are uniform. Yeah, so we require that they're all the same size. And it also doesn't matter whether you rotate around the corner or the center of the rectangle. The same idea still works. For the last set of slides, I have like a couple of things we've done experimentally. The question is whether we can still use 5 minutes to show that, or whether I should stop. Use? Yeah. Okay. So we studied different consistency models for labels. So the easiest one is to say, okay, either the label is always visible or never visible. That's the 0-1 model. Of course, it has the big advantage that there's no flickering at all. You always see it, but you cannot place many labels. The KR model says that for each label we can choose at most k active ranges. So what we've done so far was k equals 1. but you can ask what happens if we allow 2 ranges per label. And then this can show more labels because you have more flexibility, but it does flicker because labels turn on and off. And the infinity model has basically no limitations. This is like you forget about temporal coherence. This has the maximum number of labels that you can place, but it has lots of flickering. So we try to compare that using both optimal solutions that we compute for small instances using integer programming, for example. We have our 1/4 approximation implemented, and we have some simple greedy heuristics that also work here. So greedy heuristics are, you have your set of labels. While it's not empty, select one, assign the currently possible maximum possible active range, update, and repeat. So if you do greedy max, for example, you could select the label that gives you the maximum gain. So for example, the largest possible active range that you can still do. You can go for lowest cost. So if I pick that one, how much do the other ranges shrink in consequence? Or you can do best ratio, where you try to do a trade-off between the two. So this is different strategies of how to pick the next label in the greedy algorithm. And this can easily include label priorities. What instances did we use? We chose a couple of large cities of more than 50,000 inhabitants from 6 countries using OpenStreetMap data as kind of our test instances. We need to select some kind of scale for which we do that, and we use the zoom levels that Google Map uses. Our starting labeling was an unrotated, so northern-oriented labeling using a 4-position model initially, so we picked for every point one of those positions nicely. And then we computed optimal solutions with the ILP and then compared them against the maximum possible active ranges that we can gain if we forget about all the consistency. And this tells us how close to the best achievable thing we are, but how much we gain in terms of non-flickering labels. So what you can see here is that if we have a scale of say 20 kilometers, 50 kilometers, 100, then with this very strict model, you could show half of the full capacity with a 0-1 model, and in a small scale map, only 6%. Okay, so this is clearly too weak. If you go to the 1R model, where a single active range is possible, you already go over 80%. And if you have small scale map, even 94%. If you allow 2 active ranges, you have 99%, 97, 95. So this is very good. 3R gives you 99%. So it certainly does not make sense to have more than 3 active ranges. Maybe 2 is fair choice, and infinity you don't want to have. But you get there even with very consistent labeling. So that's kind of a nice result. And this plot shows the running times that we have and the qualities. So up here you find all the greedy algorithms, and on the x-axis you have running time. Greedy is very fast. This is why they are all on the left. And this is the quality measure compared to the optimum solution. So greedy achieves like 95 to 100% for these instances. The 1/4 approximation is kind of a strange algorithm because it deactivates 3/4 of the labels. Clearly it has more than 25% of the quality. That is something we proved. But yeah, by itself that doesn't make sense. But we have these blue things that we see here, which is use the 1/4 approximation and then use greedy to augment it. So this gives us a guarantee, but it also uses greedy to go as best as possible. And these are the blue disks here. They are slightly better in quality than when you do greedy alone, but you pay by a higher running time. So this is in the range of seconds, and this is kind of milliseconds. That's basically the idea here. So for summary, we've seen that the 1 range model, or maybe 2, is a reasonable compromise. We've seen that greedy heuristics produce fast and good solutions in practice. If you want to spend a little bit more time to get a solid guarantee, then the approximation things work. ILP is too slow in practice, but of course it gives you the best solutions. If you want to deal with label weights and priorities, which is important, then all these algorithms can work with it, but the approximation guarantee is lost. Okay, so this is again the references where you find some of the papers. I mean, Kevin is not here, but he has also worked a bit on dynamic labeling, showing that it's p-space complete even. And some open research questions. One is that I mentioned already, to study approximation algorithms further. For example, this one, like a PTAS for the dynamic zooming, which is still open, or use other kinds of approximation algorithms for problems like free label maximization, which is slightly different. So they use this in airspace control, for example, when they have airplanes and the names and the altitude needs to be on screen, and you cannot afford to not show a label of an airplane. That's never an option. But you can try to minimize the number of overlaps. So this would be the free label maximization problem. And then Kevin's paper showed that this is p-space complete, but it's unknown what kind of approximation results you can get. And then what is also like a very different type of labeling problem is using external labels. So those who attended ICCG have seen my talk there where we discussed static labelings of that type with labels that are far away from the points but connected with a leader line. And doing that from an algorithmic point of view for dynamic settings is also not explored. Yeah, so that would be something. Okay, thank you.
Okay, if somebody has questions.
So how do you combine the two algorithms, the greedy one with the...
So we first run the approximation algorithm, and this gives us a set of labels that we choose for which we know it's at least 25% of the optimum quality. Okay, and then we have, maybe let me go back to... So imagine this one, yeah? So this would be an approximation. We maybe chose all the gray squares and get an optimum solution here, but we show none of the white part. So if you look at a map like that, it would look like an invisible grid behind it. There's no reason not to, for example, choose this label all the time. And what greedy does is taking the deactivated white labels and doing some greedy optimization here. Yeah.
I'm thinking to add the coloring problem to this problem. Complete coloring, minimizing the color per second color.
Okay, so you mean that one color class is a set of labels that is independent, and you could swap to a different color class, and that would maybe contain the other labels in some sense.
Yeah, and minimizing the number of colors.
Yes. So people, I think I've seen some papers trying to go into that direction. So you have a number of points that you want to label, and they are too dense to put all of them. So minimize the number of pages that you need to show all labels. Yeah? So maybe the first one contains all restaurants, the next one all hotels. If you go by categories, but the coloring comes from the algorithm usually. And then maybe you can show that we can label all the points of interest in just 2 maps or just 3 maps.
Okay. Any other question? Maybe one? Okay.
how do you do the screen size,
Mhm. So the discretization is done that we, for every pair of labels, we get one of those ranges, right? So, for example, within this range, they are in conflict. So the discretization uses the endpoints of these ranges as possible starting points for labels or endpoints of label activities. Of course, if you think of any active labeling, at any angle might be one where 2 labels that are in conflict change the roles. Yeah, so one gets deactivated, and because they are in conflict, now we can show the other. But if you have such a solution, you can move it without changing the cost to one of the endpoints of the next interval. So that will give you the same quality of the solution in terms of the objective function, but now we discretize the space over which we need to optimize. No?
Okay, thank you.
We can discuss it in the afternoon. Thank you.
Okay, it's lunchtime. After lunch, I'm taking break. So it's researching session time in the afternoon. Thank you. Yeah, but maybe we should mention that it's a bit earlier than yesterday. So we just rescheduled the meeting and we start like half past. I don't know. Yeah, maybe it was half past lunch.
Usually we start at 2:30, and you say we start at 2.
Yeah.
Right?
Yeah, it's earlier than yesterday. So it starts at 2 p.m. Thank you.
Just 1 second before you get up, because during these talks with you students, I received many questions, and also Kevin, about where to find job opportunities for PhD, for postdoc in Europe. So I prepared this slide that gives you maybe a couple of hints that are important for you or interesting. Yeah. Business session, kind of. I'm not announcing anything, but just to know that the European system works differently from the American. Usually, these positions come on an individual basis because some professor received a grant and there's suddenly an opening. So you need to follow consistently over the year. If there are open positions, very few places have PhD schools where they accept 30 students every year with a deadline every year. This is, for example, the Max Planck Institute in Saarbrücken in computer science, or IST Austria, which is close to Vienna. It's not my place, but they have also geometry group there, like Herbert Edelsbrunner, for example, is at IST. For receiving these openings, I highly recommend that you subscribe to mailing lists DimaNet. This is basically discrete math and algorithm, and all the European universities post their positions here. For computational geometry, you maybe know this list, CompGeom announce, and for graph drawing, there's one called GDNet. And this is something my colleague of mine asked me to maybe put here. So he's looking for a PhD student in the algorithms group at TU Wien, working on logic and AI, SAT modeling, or speeding up algorithms using machine learning. Also using programming. So this is kind of practical and theory position. If this is something for you, approach me and I can give you more details. Yeah?
Thanks a lot.
Thank you.
Actually, that's pure about a student.